Boruvka's algorithm. We already learned about Prim's algorithm and Kruskal's algorithm. What were these algorithms used for? Both of these were greedy algorithms used for finding minimum spanning tree of weighted, connected and undirected graphs. And what about Boruvka's algorithm? The same purpose is what Boruvka's algorithm is also used for. That is, it is also a greedy algorithm. The purpose is to find minimum spanning tree and it is applied on a weighted, connected and undirected graph. So let us see how is Boruvka's algorithm different? What are the steps followed in Boruvka's algorithm? And where exactly should you make use of Boruvka's algorithm? This is what we have to learn. First of all, Boruvka's algorithm is among the earliest algorithm that were used for finding minimum spanning trees. And why is it called as Boruvka's algorithm? It is because the algorithm was first proposed by Otakar Boruvka in 1926. So this is a very old algorithm and among the earliest algorithms used for MST. This algorithm works in phases. So different from the way Prim's and Kruskal's worked, this is going to work in different phases. Phase 1, phase 2, phase 3 and so on. In each phase, it is going to find out the minimum weighted edge that is going out of each of the components that are presently formed. That is, let us say in the second phase, you are having these many components. Then, for each of these components, Boruvka's algorithm will try to find out which is the minimum weighted edge that is going out of this component to some other component. For each of the component, it is going to identify this minimum weighted edge and then it will add all of these edges into the MST, making sure that there is no cycle formed. This is the basic overview of Boruvka's algorithm. Let us try to understand in detail how Boruvka's algorithm works and what are the steps involved. Okay. So first of all, the first step is to start with each vertex as its own separate component. That is, each vertex is its own component. Its own component. This is where you start this algorithm. Each of the vertices that you have will be their own separate components. And then this is where you start finding out the outgoing edges so as to merge different components. Next step is for each component, what do you have to do? For each of the components that are present, what do you have to do? You have to find the smallest weighted edge that is connecting this component to any other component. Let us say initially you are considering only the vertices. So each vertex is its own component. What do you do for each component? Let us say this vertex is the component under consideration right now. What will you do? You will try to find out which is the smallest weighted edge that is going out of this vertex. Let us say this is the smallest weighted edge that is going out of this vertex A. What will you do next? You will move on to the next component. So each of the vertices I told you are considered as separate components now. Then for the next vertex also, you will do the same thing. You will try to find out which is the smallest weighted edge that is going out of that vertex. Similarly, you will continue this for each of the vertices. What happens then? At the end of this loop, you will know which are the smallest weighted edges corresponding to each of the components. Then third step is add all the selected edges into your MST. Add all the edges into your MST. While adding, you have to make sure that there are no cycles formed, because if a cycle is formed, it cannot be an MST. So make sure that no cycle is formed while you are adding these edges. So let us say for this particular vertex, you found this edge as the smallest outgoing. maybe for this vertex you found something like this, and for this vertex or this vertex, let us say you found this, or in some way you found a cycle like this, then it cannot become a minimum spanning tree, because spanning tree definition itself says it cannot have any cycle. So because of that, whenever you are adding edges into the MST, in that phase you should be careful not to add any edge which forms a cycle. Then what is the final step? The final step is to repeat this. That is, whatever step I told here, this is one phase of this algorithm. So when you complete one phase, you will add all edges that are part of the present phase. After this, you have to repeat the same steps till you are left with only one component, till only one component remains. Till that point, you have to keep continuing this algorithm. For example, if in this graph, after the first phase, let us say for both this vertex as well as this vertex, let us say this is the shortest edge, that is the minimum weight edge. And let us say for this vertex as well as this vertex, this is the minimum weight edge. And for this vertex, maybe this is the minimum weight edge. In this point, it is still not a spanning tree, because you still have two different components on this graph. So again, you have to continue the same process with the remaining components. For each of the components, you will try to find out which is the smallest edge that is going out. Then the question is, I just told you that you have to find the smallest weighted edge, and then you have to add such that there is no cycle formed. But how are you going to implement this? You have to find out the smallest weighted edge that is going out of each component. How exactly do you find out for each component which is the smallest weighted edge? And same way, how will you determine that it is not forming any cycle when you are adding it? So these are the bottlenecks. Let us see how can you resolve this. How do you overcome these problems? First of all, there are certain data structures that you have to use here. First data structure is disjoint set data structure. We already discussed about disjoint set in our Kruskal's algorithm lecture. And if you want to know more about disjoint sets, please go to our disjoint set lectures under data structures lecture series. There we had explained in detail about disjoint set data structure. Here you don't need all the details. Even if you have a basic idea of disjoint set, it is okay for you to continue with this lecture. So one thing is disjoint set data structure, and second thing that you need is an array which will keep track of the cheapest edge that is going out of each component. If you have both these things, you can go forward with this algorithm. Why do you need disjoint set here? Disjoint set is used for the same purpose as you used in Kruskal's algorithm. What is that purpose? In order to detect cycles. Because in disjoint set, whenever you are trying to form an edge between two vertices which are both part of the same component, that is, in disjoint set what happens? If both are part of same component, both will lead you to the same representative element. That is, if you do a find operation, you will reach the same representative element on both those vertices. If that happens, you can understand that adding this edge to your MST will form a cycle. So this is how disjoint set data structure will help you identify cycles. What about this array? This array, we'll call it as cheapest array because it will help you find out which is the cheapest edge or the smallest weighted edge that is going out of each component. So this solves both our mysteries. One mystery is in finding how to not have a cycle, that is solved with disjoint set data structure, and the other one in which you have to identify the minimum weighted edge that is going out of your component, that is solved with your cheapest array. So these two data structures will help you out in this problem. So now Now that you know these two data structures are to be used, let us see how can you rewrite this algorithm. Instead of writing like this, that for each component you have to do this, let us rewrite and understand what exactly should you do in each iteration. So keep this thing in mind and then we'll rewrite what should you do in each iteration. Okay, I'll just remove this repeat step so that we get some space here. What are we actually going to do in the algorithm? What we'll do is for each of the edge, that is, we are not going to look into each component actually when you implement. This is the logic. That is, logically, what are you going to do? You are going to see each component. For each of the component, you have to find out the smallest weighted edge that is going out, and you have to add all those smallest weighted edges into the MST. This is the logical part. But when you implement it, you implement in a different way. How do you do that? Instead of doing for each component, you do it for each edge. That is, in each phase, you will go through all the edges. Then for each of the edges, what will you do? You will find the root or the representative element of the component containing U and V. What are U and V here? Your edge is from U to V. Let us say U and V are two vertices. Then your edge E is going from vertex U to vertex V. If this is the case, then you will find the representative element of U in the disjoint set data structure, and then you will find the representative element of V in disjoint set data structure. When you do this, if both of these give you the same representative element, that means if you add this particular edge to your MST, it is going to form a cycle, which means you should not consider this edge at all. But in case it is not forming a cycle, that is, representative elements of U and V are different, that means cycle part is safe. You are not going to form any cycle. Next question is whether this edge is the smallest edge that is going out of any component or not. So for that, what are you going to do? You will update the cheapest entry. That is, what is the cheapest entry? You have a cheapest array. This is called your cheapest array. In this, you will have entry corresponding to each component. So component means initially when you are starting, you considered that each of the vertex is a separate component. So because of that, in this array, you will be having entry corresponding to each vertex. So let us say vertex 1, 2, 3 and so on. For each vertex, you will have an entry. Then in this stage, when you identify one particular edge, you will see the vertices of those edges of that edge, that is U and V. Then you will see the entry corresponding to U, and then if the entry corresponding to U is larger than whatever is the edge E, that is, as far as weight is concerned, if the weight of the entry corresponding to U is larger than whatever is that of edge E, what will you do? You will change the entry corresponding to U. The same work you have to do for V as well. So for U and V, you will update this array called cheapest. What will this tell you? Till this point, among the edges you have visited, this is the smallest edge that is present, that is going out of the component which is containing U. This is the point that you get. So you can ask me one thing here. After the first phase, each vertex is not a separate component. There may be some vertices which are together in one component, and there may be some vertices which are not together. Then what is the sense of having entry for each of the vertices? The point is, what this table is telling you is not that for each vertex this is the situation. What it is actually telling you is for the component in which this vertex is a part, this is the situation. This is what it is going to tell you. Okay. So what we'll do is Let us try to do it on a graph, because then the whole logic will be clear for you. Stepwise, it is only this. Logically, these are the steps, and when you are implementing, these are the steps. That is, while implementing, in order to decrease time complexity, you are going to run the loop once through all the edges, and in this one loop, you are going to complete the work for all the components. Otherwise, if you loop separately for each components, that is going to increase your time complexity. So in order to tackle that, while you are implementing, you are going to loop through all the edges once. And while you are doing this loop, your array, that is the cheapest array, will help you find out the corresponding values for all components. So this is how implementation side is working. What we'll do, we'll take a graph and try to find the minimum spanning tree using Boruvka's algorithm. This will make the whole thing very simple. So let us take a graph and understand. This is the easiest way to understand an algorithm. Let us say, let us take the same graph that we use for Kruskal's and Prim's. So you will be able to connect how exactly Prim's worked, how exactly Kruskal's worked, and what is the difference in the way Boruvka's is working. So we'll take the same graph. The vertices are A, B, C, D, E and F. These are the vertices. And the edges, we have an edge AB, then you have AC, you have DE, EF, DF, you have CE and BD. Then you had one more edge, which was CD. So this is the same graph that we used while explaining Kruskal's algorithm as well as Prim's algorithm. Here we are going to use the same graph and explain how step by step Boruvka's algorithm works. This one is having edge weight 1, 2, 2, 1, 3, 4, 5 and this one is having 3. This is the graph. Let us see how to apply Boruvka's algorithm. First of all, you should have an array called cheapest. What is this array? This is where you will store the value of the cheapest edge that is going out of each component. So you will have for A, B, C, D, E and F. Okay, for each of the vertices, you will have one entry in this array. You can either use an array or you can use a hash map. Both are well and good. Okay. So let us say this is your cheapest array. This is called as cheapest because it stores the values of cheapest edges that are going out of each component. Let us do phase 1. In phase 1, what happens? Each of the vertices are separate components. So A, B, C, D, E and F. Each vertex is a separate component and you don't have any edge as of now. So this is the situation. What do? You will go through each edge, and while you are going through each edge, what will you do? You will try to find out the cheapest edge that is going through each of the components. So let us start with edge AB. This one, edge AB. It is of value 5. What will you do? You will check the entry corresponding to A and the entry corresponding to B. If it is the case that you have not seen any edge till now, or if it is the case that this is the cheaper edge than what you have already seen, then you should update this cheapest array. So let us see the case of both the vertices involved in edge AB. One is A and the other is B. A, you don't have an entry for now, so you will put AB as the entry. And what is the value? Value is 5. What about B? B also doesn't have an entry. So you will put AB as the entry and the value is 5. This means for vertex A, whichever be the component in which vertex A is present, in that component, as of now, till this point among the edges that we had seen, the smallest weighted edge that is going out of that component is AB. This is what it means. Let us see the next edge. Let us say edge AC. While you are considering AC, you have to consider that AC is of edge weight 3. What happens here? For A, You are presently having 5 as the smallest, but 3 is a better value. What will you do? You will substitute this with 3. So instead of AB, you have AC, which is having value 3. And what about the other vertex, which is C? You don't have an entry as of now, so you will put AC with value 3. Let us consider the next edge. Let us say CE is the next edge. CE with value 2. This is the next one. What about the first vertex C? C is presently having AC with value 3, and presently CE is having the value 2, which is smaller than 3. What will you do? You will remove AC and make it CE with value 2. What about E? E is not having a value for now, so you will add CE with value 2. Which is the next edge to consider? Let us consider BD. If you are considering BD, it is having weight 4. What about B? B is presently having AB with value 5. So 4 is smaller than 5. So you will substitute this with BD with value 4. What about D? D is presently not having any value. You will put BD with value 4. Next edge to consider, let us say, is CD. CD is to be considered and its value is 1. We'll go to C first. CE is having value 2. So you will change it to CD with value 1. What about D? D is presently having BD with value 4. You will change it to CD with value 1. Next edge to consider is DE. DE is having value 2, that is the weight is 2. What about D? CD with value 1 is present there. 2 is not smaller than 1, because of which we don't have to change the value in D. What about E? In E, you are having CE, which is having value 2. And it is same as D, so you need not change the entry. What about the next edge? Next edge is EF. EF is having value 1. What will you do now? You will go to E. It is presently having CE, which is having value 2. EF is having value 1, which means you should substitute this with EF with value 1. F is not having anything now, so you should put EF and value 1. The last edge to consider is DF. In DF, this edge is having value 3, that is the weight 3. D and F, both vertices are having value lesser than 3, which means you don't have to alter anything. So here you can see that in single iteration through all the edges, you are able to find out the edge with smallest weight that is going out of each of the components separately. So you didn't have to run separate loop for each component. Instead, if you run one loop through all the edges, you can easily find out the smallest weighted edge that is going out of all the components. What is the next step? From this table, whichever be the smallest weighted edges that you found, you have to add all of those into your MST. So this is your MST. MST is presently not having any edges. It is in phase 1. You will add all these edges. So AC with value 3, AC with value 3, BD with value 4. So I am adding from here. Okay. From this array, I am adding BD with value 4. Next is CD with value 1, CD with value 1, CD again with value 1. So whenever you see 2 and 2 times same edge, you need to enter only once. Okay. And one more thing, whenever you are adding an edge here or here, you always have to see whether it will form a cycle with the existing MST. So this is a by default check every time, whether you are adding here in this table or into the MST, you have to make this check whether adding this particular edge will form a cycle or not. Okay. So the next one is CD is already added. EF is having value 1. EF is having value 1. This is also EF, so you don't have to do double entry. So your phase 1 is completed and this is the status of your MST at the end of phase 1. So it is still not a complete spanning tree. Why is it not a complete spanning tree now? Because it is still not a single component. Whenever you end up with a single component, you can understand that it is a complete spanning tree. That is single component connecting all the vertices. Initially, you considered each vertex as a separate component, because of which at whichever stage of algorithm you find a single component, you can say you found the minimum spanning tree. So let us say we'll move on to phase 2. So phase 2. In phase 2, what should happen? We'll clear all these entries. Again, we should repeat the same thing that we did in phase 1. First edge to consider is AB. We are going to go through the same edges again. Let us see how the algorithm differs, or the way the algorithm functions differs when you go through the same edges in phase 2. Let us say AB is the edge. It is having value 5. So in phase 1, we ignored this edge. In phase 2, what happens? In phase 2, when you see AB, if you add AB, what will happen here? If you add AB here, it will form a cycle with the existing MST. Because of that, AB won't be considered while you are adding at all. And how do you understand this? Here I showed you because you have a picture of the graph, and it is easy to show that if you connect this AB here, it will form a cycle. But actually when you are implementing, you have to use disjoint set data structure, and then you should find out the representative element corresponding to vertex A and the representative element corresponding to vertex B. In this case, because both A and B are from the same component, representative element of A as well as the representative element of B will be same. Whenever the representative element of both vertices are same, you should understand that if you add this edge, it will form a cycle, and because of that, you should not add this edge. So because of this, AB is ignored. Next is AC. What about AC? AC is already part of this MST. So again, if you see the representative element of A and representative element of C, what will you find out? You'll find out that both the representative elements are same. How do you find this representative element? You have to do a find operation on the disjoint set data structure. So when you do a find operation, you will find representative element of both these. And whenever you are adding an edge onto MST, you have to be careful that make sure you do a union operation in the disjoint set data structure. Otherwise, it won't be able to record that edge. So this is how it is done. AC is also done. Next is, let us say BD. BD, it's also part of the MST. Both B and D will have same representative element. CD is also part of MST. Let us see CE. What about CE? CE is having value 2. C is from a component. E is from a different component, because of which C and E will give you different representative elements if you do a find operation on C and E. So then what should you do? You should add the entry in this array. Corresponding to C, you will add CE with value 2. Similarly, on E also you will add CE with value 2. Next edges, DE. What about DE? DE, again, D is in one component, E is in another component, because of which if you do a find operation on D and a find operation on E, you will end up with different representative elements, which means they are from different components and will not form a cycle. What will you do then? You will see the vertex D. Corresponding to vertex D, there is no entry. So you will add DE and the value of edges 2. What about vertex E? Vertex E is already having a value which is 2, so you don't have to change it. What is the next step? You have to consider other edges. Let us say DF and EF. EF is already part of MST. DF is remaining. What will happen when you see DF? For DF, the value is 3. For D, it is in one component, F is in another component, because of which you can add this value into the array. Corresponding to D, you already have value 2, which is smaller than 3, because of which you don't have to add here. What about F? There is no entry and you will add DF with value 3. Next step is to add all these edges onto MST and make sure that you have to do find operation on both the vertices so that it do not form a cycle. Okay. So if you do CE, edge CE can be added safely here. If you do find operation, C and E will give you different components. So you can do CE here with value 2. Edge weight is 2. Which is the next one? Next one is DE. If you add DE here, what will happen? It will form a cycle. How do you identify cycle? You do find operation on D and E. You will get same representative element. Because of which you will understand that adding this will form a cycle and you should not add this edge. CE is already added. What about DF? DF, if you add DF, it will form a cycle. So this also is the same case as DE. That is, if you see find operation result on D and F, you will understand that you should not be adding this value. So at this point, your phase 2 is completed. And most importantly, at the end of this phase 2, if you see this graph, it is an MST now because all the vertices are connected and you don't have any cycles. How do you identify this? You have to do find operation and on each and every vertex, and if all of them gives you the same representative element, that means you already have an MST. There is only one connected component. So this is how Boruvka's algorithm works. The next question is, what are the time and space complexities of Boruvka's algorithm? So let us analyze time and space complexities now. From the algorithm that we have written, if you see for the time complexity, let us understand this by understanding how many times each operation is done. So if you see, you are looping through all the edges. So order of each time is required in order to simply loop through all the edges. Next question is, what are you doing inside each loop? That is, looping through each edges takes order of E, and then in each loop, what are you doing? First thing, you are trying to find out representative element of U and V. So this is a find operation. In disjoint set data structure lecture, we had explained that find operation on a disjoint set will take order of alpha of V, where alpha is Ackermann constant. So we had already said that for all practical purposes, this Ackermann function will give you a constant value. So let us ignore this value for now, considering it as a constant. So let us say this is order of 1. It is actually order of alpha of V. It is a constant for all practical purposes. So this we had explained in detail in path compression lecture in data structure lecture series. So this is the case. For now, just understand that this is a constant. So let us say it is a constant time operation. And then for U and V, you have to update the cheapest array entry. So this will also take only order of 1 because you have to go to an entry in array and update. So from this analysis, you can understand that each loop will take only order of E time. So keep in mind that we are considering this as a constant value. So order of E time is taken by each phase. So in one phase, you will take order of E time. Next question is, how many phases will you have? So if you think logically, in each of your phases, your number of components will decrease by at least half. At least your number of components will become half. How is it? Because let us say initially all your components are vertices. Each vertex will have at least one edge which is outgoing, which means you will be connecting two components. Each of the edges will be connecting two components. And in worst case, what can happen? For two edges, two vertices, you will have same edge as the lowest one. But even if that is the case, still you will have two vertices connected, which means previously if you had V components corresponding to V vertices, you will at least decrease the number of components by V by 2. So if that is the case, then how many steps will it take to reach one component? That is, initially you are having V components. After one phase you are having V by 2 components, then V by 4 components. Like this, if you are going, then how many steps will it take for you to reach only one component, such that total number of components is 1? So this in the analysis that we explained in time complexity lecture, we know that this takes log v steps. So order of log v steps is what it takes to reach one component. What is the importance of reaching one component? The importance is that whenever you have only one component, you already found the MST. So this is where the algorithm stops, which means order of E is the time taken for each phase, and you may have a maximum of order of log V phases, which means the total time complexity is order of E into log V. So order of E log V is the time complexity of Boruvka's algorithm. And what about the space complexity? What are the additional spaces you are using? One is you are using disjoint set data structure. So disjoint set, you have one for each vertex to start with, and then you may be unifying many of those, which means you will have V nodes, you will take order of V space. Then you should be having an array, that is the array to store cheapest element, cheapest edge that is going out of each vertex, each component. So for that, you will again have order of V space, so which is same as this. So if you see by this way, total space used by Boruvka's algorithm is order of V. And according to this, whatever analysis we have done, we can conclude that the time complexity is order of E log V and space complexity is order of V.